Hello everyone, today we are back with another medium level lead code question, and in this question we'll learn how to calculate things that don't exist. What do I mean by this? I mean by this is that we are required to find the width of a given binary tree. For example, this is the binary tree you can see. So what is the maximum width of this? The width at this level is 2. The width at this level is 4, not 3, 4, because you have to count the null value here. This, the first thing that strikes to the mind is then definitely it's going to be the last level, which is going to have the maximum width, but not. That's not the case because, like, let's say if 3 and 9 were not present. Okay, so at the last level, the only node was 5. So that is not having the maximum width. Maximum width would be at the first level, that is between 3 and 2. So that is the maximum width is the distance between, including null, the distance between the extreme nodes of a level. So it is 3 and 2. So these are the extreme nodes. So distance between them, including them, is 2. Here 5 and 9. The distance between them, including null and 3, is 4. So that is what we call as the maximum width. So for example, in this question, this is a tricky one. Here, the maximum width is going to be at the last level again. The reason being that 3 will have a null, that null will have two more nulls. Okay, 5 will have a null, that is one. 3 will have a null, and that null will have two more nulls. So, total 4. Similarly, from this side, 2 will have a null, that null will have two more nulls. So, that is plus 2, and then we have one more 7, that is 7. So total width would be 7. Basically, between the extreme nodes, that is 6 and 7, whatever, even the null values are present, we have to count them. If it is a null value, then also we have to count. If it is a normal integer value, then also we have to count. Now I'll quickly discuss few of the funny ways which I tried to solve this. So let's say in this particular example itself, we'll take 1325. Okay, 1325 and 9797, and this is going to be 6. So here what we are going to do, what I tried doing was I created nodes. I basically created, I saw, okay, there is nothing here. I created -101 because this is not the permitted value. And I see here also there's no node. We just create 101. And we initially only we have calculated the maximum depth, and we don't go beyond the maximum depth. Here this we also traverse to this new node and we create one more 101, we create one more 101. Similarly, from 2 there will be one node here, and then again 2 -101 -101. Then what I did was I performed a level order traversal. I performed a level order traversal, and for each level, like let's say for third level we have 5, for, or we can, if we start from 0, thus for the second level we have 5 -101 -101 and 9. So I calculate the length from the leftmost normal integer, that is not -101, and the rightmost normal integer, that is 9, including -101, and that is I take as the width of this level. Similarly here I calculate 6 and all the -101 that fall between them, and 7. So that is 7. This is the maximum length. This was the correct solution, but what it did was it used more memory than what it is supposed to. We created so many nodes. Okay, so I actually surpassed the memory limit instead of the time limit, which I generally do. So I crossed the memory limit. Then I thought, why to populate this? Why to populate it with -101? Why can't I see a none? I see a none. It's Python, so I see a none, and I see a none. And if it is yet not the last level, it is not yet not the maximum depth, then even after seeing none, I go to next. I call a recursive stack, which goes to two more nuns. Okay, which goes to two more runs, and I calculate them as well. If I have seen a value on the left for a level, then I calculate that particular null or that particular null as well, none as well. And once I see the last value, since I've calculated how many values are present at each level. So once I see the last value, I stop calculating the none. Okay, so this also was giving the solution, but this time I crossed the time limit, which I generally do. So, apart from that, the correct solution to this is very interesting, very good. It's a very basic concept. I believe if I would have tried this particular thing in while I didn't try it in my college days, if I tried it after reading the theory of binary tree, then it would have been easier. So the theory simply says that if the index of the parent is I, the index of the left node is I into 2, and the index of the right node is I into 2 plus 1. Okay, simple as that. We have to remember this. This is a very basic theory. If we start calculating, we allot them nodes and all. So we'll realize that yeah, this is correct, because it will accommodate all the things on the left and then all the nodes or any siblings of this particular node, and then it will come here, and this basically satisfies the rule. Um, so, and since we are considering it to be a complete binary tree, that's why this is possible. So we basically want even null, we are assuming that null is present. So that's why we can calculate that. We can think that it is a complete binary tree. So what we do here is we simply simply perform a BFS. So we know in BFS we have a queue. So let's start from an example. Let's start from this example itself. 1, 3, 2, 5, 9, 6, and 7. So it is 6 and this is 7. Beautiful. So what we do is we initially put 1, the first node, along with 0. This is a queue. Okay. And then what we do is we visit this particular node in the queue. Okay, this is a starting point. We visit here, and what we do is we check the leftmost node and the rightmost node. Okay, so the leftmost node is 3. So we add 3, and we are maintaining a node along as a tuple. So this per using index. So this particular index is basically we starting the root node with 0 index. The left node of that 0 index will be again the value, or the node is 3, and the index for that is 2 into what was the no index for the parent. So that is 0 again. So we add 0 here. The queue has increased. This is not the boundary of the queue. Now again we go to the right node and we add 2, and 2 into the index of the parent node plus 1. So that is going to be 1. Okay. So in the first loop, we just saw the element of the queue. Then that is done. Now we go to the next level. Okay. And at the next level, what we do is we again start seeing the children's of this particular node, and we start appending it. First what we do is we take the see be in the first iteration we found what are the nodes at the level 1. Okay, so when we go to the next iteration, what we do, we first calculate that what was the width of the last level. So the width of the last level is basically index of the rightmost the tuple and index of the first where the start value is. We have to basically find the difference of that index and add 1 to it. 0 plus 1, so this is equal to 2. Okay, so the length of this level was 2. This is we calculated this when we were here. Okay, because at that point only we have populated this when we reached here, basically when we reached to this level, that's when we calculated, okay, what was the length of this particular level. Okay, so because that's when we know like what are the tuples that are present at this level. Similarly, what now you'll see what happens. Now we know what is the length we have to traverse. We initially calculated, okay, this is the length we have to travel. We have to start. We have to begin from start, and we have to move up till the like let's say initially itself we know start is at 1. It is at 1, and the end or the length of the queue is 3. Okay, so we have to travel from 1 to 3, 3 excluded, 3 is not included, so 1 2, basically this 2. So for this level we'll visit the tuple 1 and the tuple 2. So we go to the left node of this particular left child of this particular node, and we add it to the queue. So it becomes 1 0. We are, since start has moved ahead from this, so 1 0 is that just present, it is no more used. 3 0, we have 2 1, and the left node for this is 5. Left node for 3 is 5 0. There is no right node. Similarly, left, there is no left node for 2 1, and the right node is 9. Then 2 into 1 plus 1, that is 3. Okay. And by this time, so when we reach to this level, the start has, I increment the start to the I plus 1. At the end of the loop, I increment it to I plus 1. The start reaches here. So once I reach at this level, I again calculate what is the width of this level. So how do we calculate? 3 minus 0, 3 minus 0 plus 1, that is 4. So you can see, if I add a null over here and a null over here, so length of this particular level is 4. Similarly, now we traverse the children of 5 and 9, and we will find 6 as 6 and node 0, and 7 as 7 as 3 into, since this is also the left node, 3 into 2, so that is 6, right? 6, yeah. So this level is done. What we do is we come to this level 6 7. We come to, where's my cursor? This is the level, and we subtract the index, that is 6 minus 0 plus 1, that is 7. And we are iteratively, in each iteration, we are updating the maximum of the width. So 7 was the maximum, and that is what will be returned. Now this is reduced, and we are no more trying to find the things that don't exist or count the things that don't exist, which I tried to calculate the nuns as well. I tried to populate them, but those are not the ways. So this is the way. And so what happens here is, in these types of questions, general way of us solving any binary tree question is to traverse, but we don't generally think about the indexes and all. So that's what I followed initially. I thought of, okay, I'll travel, I'll count the none, or I'll populate it with some value. But that is not the way. We have to go through the basics. The basics are that we can calculate the nodes, or the index of the children nodes using the parent node, and that's what we do. We maintain an index. We create a queue of tuples, where the first value is the node and the second value is the index of that node. And that index can be used, or we can basically say that index accommodates the null as well. So if the base is like, let's say 2, this left side will have um no, this left side will have 4, because it's 2 into 2, and this will have 5. Okay, so anything that will come, or let's say here we have something called as 3, and it basically will not be 3, but yeah, it at the least it will be, no, it will be 3, yeah. So if we have one index here, one index here, the index will for this is will be 6, and for this will be 7. So you can see the distance between these can be find, though this is not present. We don't need to count them. We have the index, and we can directly subtract the index and use it for counting the width. So this is the correct way to do it, and this is the thing. We basically performed a BFS. We can call this question to be BFS using indexing for each node in a tree. Okay, using indexing for each node in a tree. So this is the way. Hope you found it interesting, and you found it very the experience to be learning. And if you find it so, then please like, subscribe, and keep following this channel. Thanks a lot.